Today, we are exploring the principle of mass transfer and diffusion. We will analyze the fundamental mechanisms that govern the transport of chemical species, the governing equations behind the molecular transport, and the predictive models used to quantify this phenomena in industrial process. In chemical engineering, mass transport represents the migration of species through a mixture. It is one of the three pillars of transport phenomena. Just as momentum transport follows Newton's law, heat transport follows Fourier's law, mass transport is primarily governed by Fick's law. The moment is driven by a potential gradient, most commonly a concentration gradient, though temperature and pressure can also act as driving forces. The diffusion coefficient or DAB is the proportionality constant that quantifies the ease with which molecule A moves through medium B. The magnitude of DAB varies drastically across phases. In gas phase, high molecular mean free paths result in high diffusivity. In liquid, molecular interaction and density increases resistance, while in solids, diffusion is restricted to lattice vibrations and defects, resulting in coefficients many orders of magnitude lower. Fick's first law of diffusion. For a system at steady state, we utilize Fick's first law. It defines the molar flux Ja as product of diffusivity and negative concentration gradient. This mathematical relationship confirms that a species will spontaneously diffuse from a region of high chemical potential to a region of low chemical potential to achieve a thermodynamic equilibrium. Total molar flux and advection. In practical engineering applications, we must account for both molecular diffusion and bulk motion or advection. The total molecular flux Na is a vector sum. It includes diffusal flux relative to molar average velocity and the convective flux, which is the species contribution to the bulk flow of entire fluid stream. Now we will study the special cases of steady state diffusion. We categorize diffusion into specific limiting cases for simplified analysis. Equimolar counter diffusion, also known as EMCD, occurs when the molar fluxes of two species are equal and opposite, commonly seen in distillation. In contrast, diffusion of A through stagnant B occurs when one component is stationary, typically in evaporation process where vapor diffuses through a non-condensable gas like air. Now we'll look into the fixed second law, which is followed at the unsteady state. When concentration profile evolve over time, we transition to fixed second law. By performing the differential mass balance over a control volume, we derive a partial differential equation PDE. This law allows us to predict the penetration of a solute into medium as a function of both position and time, which is critical for batch processing and environmental modeling. Gas phase diffusivity estimation. To estimate the diffusivity in gases, we rely on the kinetic theory of gases. The Chapman-Insong equation is the theoretical standard, while the Fuller-Giddings method is a widely empirical alternative. These methods show that gas diffusivity is highly sensitive to temperature, increasing at a rate of T raised to 1.5 to T raised to 1.75 and is inversely proportional to the total system pressure. Estimation of liquid diffusivity. Liquid diffusion is more complex due to the shorter distance between molecules and stronger intermolecular forces. We utilize the Stokes-Einstein equation for large spherical molecules and the Wilke-Chang equation for the small molecules in dilute solutions. In these models, solvent viscosity is the dominant factor. As viscosity increases, the hydrodynamic drag on the solute increases, significantly reducing the rate of mass transfer.
In solids, atom move via vacancy or interstitial mechanism, basically jumping into holes in the lattice. Unlike gases, solid diffusion is extremely sensitive to heat and follows an Arrhenius exponential relationship with temperature. Sometimes diffusion gets weird. Knudsen diffusion happens in tiny pores where molecules hit walls more than each other. We also have Graham's law, which reminds us that lighter molecules like hydrogen move much faster than heavier ones like oxygen. Maxwell-Stephens diffusion. When dealing with complex mixtures or non-ideal systems, simple fiction law aren't enough. The Maxwell-Stephen approaches treats diffusion as a balance between the driving force and the frictional resistance between different molecules. Eddy turbulent diffusion. In real world, like ocean or pipes, turbulence does the heavy lifting. Eddy turbulent uses swirling fluid motion to make substance orders of magnitude faster than random molecules motion ever could. The two film theory assume a thin stagnant film on both sides of an interface. We use mass transfer coefficient to calculate how fast a solute jumps from gas phase into the liquid phase. Advanced transfer theories. Traditional film theory is a bit static. Higgins penetration theory and Danckwert's surface renewal theory are more realistic. They account for fluid elements constantly being replaced at the interface, which is perfect for modeling bubbles or falling films. Now let's talk numbers, especially dimensionless numbers. These are the tools engineers use to scale up experiments and predict transport phenomena across different systems. For a non-electrolyte liquid, the Scheibel equation is go-to imperial collection. It links diffusivity to temperature and viscosity, while according to molar volume of the solute. Here is the formula of Scheibel equation. How do mixture behave? The Wigner's equation estimate mutual diffusivity based on mole fractions of component in a 50-50 mixture. The diffusivity is simple, the geometric mean of two components, infinite dilution values. Electrolytes are special because they have to maintain electrical neutrality. The Nernst-Hartley equation calculates a combined diffusivity that ensures that positive and negative ions stay together while moving. Intrinsic property ratios. To characterize transport, we use the Schmidt number, which is a ratio of kinematic viscosity to molecular diffusivity. This tells us the relative thickness of hydrodynamic versus the concentration boundary layer. Similarly, the Lewis number relates thermal diffusivity to mass diffusivity, essential for simultaneous heat and mass transfer analysis. Analysis of transport rates. The Sherwood number represents the ratio of convective mass transfer to molecular diffusion. It is the mass transfer analog to the Nusselt number. The Peclet number, defined as Re into Se, quantifies the relative contribution of advection to diffusion. High Peclet number indicate that the bulk flow dominates the transport process. In chemical engineering design, we used correlations to determine the mass transfer coefficient. By relating the Sherwood number to Reynolds and Schmidt numbers, we can predict transport rates in pipes or packed beds. We also utilize the Standard number, which expresses the ratio of total mass transfer to the convective capacity of the fluid. When diffusion is coupled with a chemical reaction, the Dumkohler number is critical. It compares the reaction rate to the mass transfer rate. For unsteady state diffusion, we employ the mass transfer Fourier number. This dimensionless number time parameter allows us to solve the transient version of fixed second law for varying geometrics. The buoyancy driven transport. In systems without forced flow, we look at the natural convection. This is governed by the Grashof number, which relates buoyancy forces caused by concentration induced density gradients to viscous forces. When multiplied by the Schmidt number, it gives us the Rayleigh number, defining the stability and the rate of transport in stagnant fluids. This table serves as a rigorous reference for the transport dimensionless groups. By identifying the regime, whether it is dominated by gravity, momentum, or molecular diffusion, engineers can select the appropriate Chilton-Colburn J-factor analogies to bridge the gap between heat, mass, and momentum transfer. Advanced transport phenomena, diffusion models, and correlations. We now transition into more complex consecutive equations. These models move beyond binary fiction assumptions to address non-ideal solutions, multi-component mixtures, and systems where external fields like electrical or thermal gradients provide the primary driving force for flux. Mass transfer is not always driven by a concentration gradient. Electrodiffusion accounts for migration of species in an electric field. Interdiffusion involves the mutual transport of atoms in solid state alloys. Finally, the Soret effect describes mass flux induced by temperature gradient known as thermal diffusion. The Nernst-Planck equation is the fundamental flux expression for charged species. It extends Fick's law by adding electrophoretic migration term. This term is proportional to the valency of the ion, the Faraday constant, and the gradient of the local electrostatic potential, allowing for a rigorous description of the ion transport in electrolytes. When applying the Nernst-Planck model, we assume a dilute solution and often neglect bulk fluid motion to focus on the migration-diffusion coupling. This equation is a mathematical foundation for analyzing concentration polarization in fuel cells, batteries, and reserve osmosis membranes.
Have interdiffusion in solids. In solid alloys like steel, we use the Darkin equation. It calculates an interdiffusion coefficient by looking at how two different types of metal atoms swap places based on their individual speeds and concentrations. This equation describes diffusion in a binary system, such as alloys, where two different atomic species move simultaneously. The theoretical implications. The overall speed of the mixture depends on how fast each component is and how much of it is there. It is the standard for material scientists studying how alloys form and transform. Next, we have the Soret effect. This is a phenomena where heat causes mass separation. If we have a hot side and a cold side, particles will migrate from one to another, creating a concentration difference purely from temperature gap. To model this, we add a thermal diffusion term dt to the flux equation. This is used in high-tech fields like isotope separation, polymer solutions, and even studying petroleum reservoirs. In gas phase diffusion, gases are best explained by Bird-Sport's equation. It assumes gas molecules are just random balls colliding in space. It is built on the idea that gases are binary of two types and behave ideally. Three things matter for gases: molecular size, temperature, and pressure. Bigger molecules collide more and move slower. Temperature. Higher the temperature, higher is the speed of the molecules. Higher the pressure is more the number of collisions, yet slower the diffusion. Next, we have the Lie correlations. The Lie correlation is a simplified practical version of the complex gas theories. We use it to quickly estimate gas diffusion at low pressures using basic units like Kelvin and atmospheres. To use these gas formulas, we need molecular IDs like the collision diameter, how big the molecule is, and the collision integral, how it is affecting the bounce. These allow us to predict speeds for any gas pair. For liquid phase diffusion, we have the Minhas equation. For solid solutes in solvents like paraffins or hydrocarbons, we use the Minhas model. This is critical for designing chemical reactors and extraction units where liquids are the main medium. It also has some other applications in chemical reaction engineering, separation processes, extraction and absorption, and design of reactors. The math here shows that diffusivity goes up with temperature but gets crushed by high viscosity and large molecular size. It is the standard for predicting movement in paraffin system. To wrap this up, we have the summary of different transport modes. We have, for ionic solutions, we have the Nernst-Planck equation where the key driving force is concentration gradient along with electric field. For solid alloys, we have the Darkin equation with key driving force as chemical potential and primary dependency over mole fractions. For thermal mixtures, we have the Soret effect where the key driving force is the temperature gradient and the primary dependency is over thermal diffusivity coefficient dt. For binary gases at low pressure, we have the Lie correlation, where the kinetic energy is the driving force and it is directly proportional to the temperature and inversely proportional to pressure. For liquids, we have the Minhas relation. The driving force here is hydrodynamic flow, and it is directly proportional to viscosity and molar volume. Thank you.